Hey everyone, and welcome. Today we're tackling a Leetcode problem called total characters in string after transformations 2. It sounds a bit like a mouthful, but don't worry, we'll break it down step by step. The main idea is we start with a string, and we transform it multiple times. Our goal is to find out how long the string becomes after all those changes. Ready? Let's dive in. So here's the problem description. We're given an initial string, let's call it. We also get a number which tells us how many times we need to perform a transformation. And finally, there's a list of numbers, let's call it, which has 26 entries, one for each letter of the alphabet. Now, what's a transformation? For every character in our current string, say, the character we look up the value in that corresponds to, let's say that value is 3. This means we'll be replaced by the next 3 consecutive characters in the alphabet. So would become, if the character was and its value was 3, would transform into wrapping around the alphabet. We do this for all characters in the string, for rounds of transformations. The final answer we need is the total length of the string after exactly transformations. And since this length can get super long, we need to return it modulo 10 to the power of 9 plus 7. Let's walk through the example given. Our starting string is, the number of transformations is 2. And the list mostly contains ones, but the value 4 is 2. First transformation. The string uses its value, which is 1. So becomes the next 1 character. Uses its value 1. Becomes uses its value 1. Becomes each uses its value 1. So each becomes after this first round, our string is its length is 5. Second transformation. Now our string is becomes now for the value 4 is 2. So becomes the next 2 characters. After comes then, so each becomes putting it all together. The string is, the length is 7, and that's our answer. Okay, what's the first idea that pops into mind? We could just do what the problem says, right? Simulate each transformation step by step. For steps, we go through the string, replace each character, and build a new string. But hold on, can be huge, up to 10 to the power of 9. And the string length itself can grow. If we simulate times, and each time we process a potentially long string where each character might produce many new characters, well, that's going to be way too slow. We'd be waiting forever for an answer. We probably need a more clever approach, especially for those large values. So, direct simulation is out if is large. Let's think. Instead of building the actual string, what if we just keep track of how many of each character we have? You know, like 5, 3, and so on. Now, how do the counts of each character change after one transformation? For example, if a nakar changes into walatani, then 1 contributes 1 to the count, and 1 to the count in the next step. This relationship, how old character counts affect new character counts, sounds like something we can capture systematically. In fact, this kind of transformation on a set of counts can often be represented by a matrix. Exactly. Let's imagine a list, or a vector, that holds the counts of each character, through, after, say, transformations. We can call this now, we can define a special 26 by 26 matrix. Let's call it. This matrix will be our rulebook. An entry in this matrix, say at row and column, will tell us how many of character are produced, if we start with a single character, and apply one transformation. With this matrix we can find the character counts after the next step, by multiplying with the current counts vector, so is equal to times v, underscore k minus 1. This means if we want the counts after transformations which we can call, it's just raised to the power of multiplied by our initial character counts. And the best part? We can calculate to the power of very quickly using a technique called matrix exponentiation by squaring, even if is enormous. This is the key. Alright, here's the Python code that puts this matrix idea into action. I know, it might look like a fair bit of code, but don't let it scare you. We'll walk through the main parts nice and slowly, explaining what each piece does in plain English. The core ideas are what we just talked about, setting up counts, building that transformation matrix, powering it up, and then getting our final answer. First up we have a little helper class, let's call it, to represent our matrices. When we create an object, it can either be a zero matrix or an identity matrix. That's a special matrix with ones on the diagonal, and zeros everywhere else. The important part here is the method. This is how we multiply 2 matrices together. For each cell in the resulting matrix, we do a kind of row from the first matrix meets column from the second matrix operation. We multiply corresponding elements and add them up, making sure to use our modulus, that big prime number, at each step to keep the numbers manageable. Next we have the quote, matrix power function. This is where the magic for handling large values happens. Instead of multiplying our base matrix by itself times, which would be too slow, we use a method called exponentiation by squaring. Think of it like this. If we need to calculate, say, m to the power of 8, instead of 7 multiplications we can do m squared, then square that to get m to the 4th, then square that to get m to the 8th. Only 3 multiplications. This function cleverly uses the binary representation of the exponent to combine these squared powers efficiently. It starts with an identity matrix for the result and keeps track of the current power of our base matrix, squaring it each time. If a bit in the exponent is set, it multiplies the result by that current power. This is much faster. Alright, now inside our main function, the first thing we do is figure out the initial counts of each character in our starting string. We create a list, let's call it versus 0, of size 26, initialized to all zeros. Then we loop through each character in callis. For each character we find its position in the alphabet, like is 0, is 1, and so on, and increment the count at that position in our versus 0 list. Pretty straightforward. This is a crucial step, building our transformation matrix, which we called M matrix. Remember, an entry at M matrix row column tells us how many of character are produced from one character. So we loop through each possible original character. From 2, we look up its value, which tells us how many new characters it will form. Let's call this. If this number is huge, say bigger than 26, the character will wrap around the alphabet multiple times. So we calculate how many times it goes through to, and what's left over. For every character in the alphabet it will be produced times by our torus, so we set those entries in the M matrix. Then, for a nyafora we add 1 to the count, for each specific character that's formed in that partial cycle. And of course, all these additions are done using our special modulus number. Now we're on the home stretch. We have our transformation matrix and our initial counts, versus 0. We also have the number of transformations. First, we call our function to calculate raised to the power of. This gives us a new matrix, let's call it. This matrix embodies all transformations in one go. Next we multiply this matrix by our initial counts vector, versus 0. This gives us the final counts of each character after transformations. We store this in. Finally, to get the total length of the string, we just sum up all the counts in our vector. Again, we make sure to apply the modulus to this sum. And that's our answer. So how efficient is this matrix approach? Let's talk complexity. The most intensive part is calculating to the power of matrix multiplication of 2, say, k by k matrices, takes about k cubed operations. And the matrix exponentiation does about log t of these multiplications, so that's roughly k cubed times log t. Here k is our alphabet size, which is fixed at 26. We also do some initial work to count characters in string s, which is proportional to the length of s. And some final calculations. Overall, the time complexity is dominated by that matrix exponentiation part. Since 26 cubed is a constant, it's very efficient, especially when is large. For space, we need to store a few 26 by 26 matrices, so the space complexity is proportional to the alphabet size squared. This is also quite modest. So let's recap the main ideas. The problem asked for the total length of a string after many transformations. Doing it step by step or simulating directly would be too slow if the number of transformations is very large. The trick was to shift our focus from the string itself to the counts of each character. We saw that how these counts change from one step to the next can be described by a transformation matrix. Then, to find the counts after steps, we could raise this matrix to the power of, and multiply it by the initial counts. And the secret weapon for calculating quo to the power of t quickly was matrix exponentiation by squaring. Once we have the final counts of all characters, we just add them up, remembering that special modulus number, to get our final answer. Hope that breakdown made sense and helped you understand how to tackle this problem. If it was useful, feel free to hit that like button, maybe subscribe for more Leetcode explanations, or drop a comment if you have any questions or other ways to solve it. And hey, if you're feeling extra generous, there's always the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next one.